Okay, we're still on dollar cost averaging. It was a good game last night. The Heat really romped in the fourth quarter. So it's 1-1 in the series. Okay, we did two cases. We did a case with we had the variable share price that fell in the end, variable share price that rose in the end. And let's do a case 3 here. Okay, and here we'll do constantly rising share price. Okay, so again, we're going to take a 4-month period, and we'll look at our price per share. And this, of course, is in dollars. And number of shares purchased for dollar cost averaging. Remember, the fixed number of shares always has the same number of shares purchased each period. So here we have 4 months again. And let's say that we start off with $20 a share in month 1, then we go up to $25 a share, then we go up to $33.33 per share in month 3, and finally we end up with $40 a share on month 4. So with our $200, remember our budget is $200. Our initial budget in period 1 equals $200. Okay, so in dollar cost average, we're going to spend that $200 each period. So, and if the share price is $20 a share, then we can clearly purchase 10 shares the first period. If it's $25 a share, then we can only purchase 8 on the second period. It's $33.33 a share. We can purchase 6 on the third period. And for $40 a share, we can only purchase 5. So the sum of the number of shares that we purchased, dollar cost averaging, is 29. So now it's very easy to look at the rate of return for dollar cost averaging. So let's do that first. Okay, so what is our portfolio value at month 4? We could say the end of month 4, but it matters not. Remember, we have a total of 29 shares at $40 a share. So that equals $1,160. That's the value of our portfolio. And the cost of our portfolio, the cost for dollar cost averaging is easy because we use $200,000 every period. So the cost is equal to $800, just 4 times 200. So our rate of return is what? Is the value, so 1160, over our total cost, 800, minus 1 times 100. And this, of course, is in percentages. So here we have 45% rate of return, a pretty good rate of return. Now let's look at a fixed number of shares. And we saw that in the first period, we purchased 10 shares with our $200. So this is going to equal 10 shares per month. Okay. So the value at month 4 equals what? Equals 40 shares, because we purchased 10 shares per month, times $40 a share, equals $1,600. And our cost is the following. In the first month, it's $200. In the second month, to purchase 10 shares, it's $250. In the third month, it's $333 and a third dollars. And in the fourth month, it's $400. So let's put that here. This is 1, 2, 3, 4. And this works out to be $1,183 and a third dollars. So our rate of return is what? Is the value, the $1,600, over our cost, 183 and a third, minus 1 times 100, because we want percentages here. So it equals 35.25%, which is clearly less than 45%. So again, dollar cost averaging does better in terms of the rate of return. In fact, dollar cost averaging always does better, at least as good as fixed number of shares. The only time it would be equal if we would have the same cost for each period. Then both would be exactly equal. Now, let's do, I think we're going to do one more. And then we're just going to summarize some. Oh, no, good. Let's look at other cases. And we're going to do a summary of other cases. I'll do a month. 1, 2, 3, 4. And then we'll consider price per share. In dollars. Okay, and then we'll look at case 4. Case 4 will be constantly falling share price, 20, 16 and 2/3, 10 and 5. So this is constantly falling share price. And then let's look at one that takes share price as constant and then rises at the end. So we'll go 20, 20, 20, and then let it jump up to 50. And finally, we'll consider a case where we have constant share price that falls at the end. 20, 20, 20, and 10. Okay. For homework, let's have it due this Friday, okay? Is calculate R, the rate of return for dollar cost averaging and fixed number of shares for these 3 cases. Okay. We could go on and do cases, but all these numerical cases will give us the same result. Unless the share price is constant through all 4 months, the dollar cost averaging will always be better. If it's constant, then dollar cost averaging and fixed number of shares will be exactly the same. Okay, now, for extra credit, for this Friday, prove that dollar cost averaging is always at least as good or better in terms of our rate of return than buying a fixed number of shares. Each period. Okay. And to do this, why don't we call this a hint? To do this, use the arithmetic mean geometric mean we could call this x bar A. We could call this guy x bar g. Harmonic mean we could call this guy x bar h. Inequality. Okay, so you might remember this. You might have had this in high school or as an undergraduate. Let's define this. This inequality says the following. It says that this inequality, for this inequality, we say what? We say that the arithmetic mean is always greater than or equal to the geometric mean is always greater than or equal to the harmonic mean. Okay. Now, in the proof, we're really going to use the arithmetic mean and the harmonic mean here. These are the two things we use in our proof. Okay. So let's look at this. Let's look at some definitions. Suppose that we have n values. You could call these observations. Okay. x1 through xn. Then the arithmetic mean is just our traditional mean, equals x bar a equals 1 over n onto sum I equals 1 to n xi. Okay. So that's our arithmetic mean. Our geometric mean is the following. X bar g equals the nth root of x1 times x2 all the way out until xn. Okay. And the harmonic mean equals n over 1 over x1 plus 1 over x2 all the way out to plus 1 over xn here. Okay. Now, to make it easier for Shauna to grade this, let's introduce some common notation, okay? Okay, B equal the budget each period. Remember that that budget is the same for both dollar cost averaging and fixed number of shares. And let SI, little si, equal the share price in period I. It goes from 1 to n. N is our total number of periods. Then the rate of return equals the value of our portfolio at end of period n over the total cost for the n periods. Let's put parentheses around that. Minus 1 times 100, of course, in percentage. So please use that notation. It'll be a lot easier to grade this. And what we do then is we calculate this R for both dollar cost averaging and for a fixed number of shares. And what you'll see is that this is really relates to the arithmetic mean, harmonic mean inequality. Okay. Now, let's jump to another important thing, which is the Markowitz model. And this Markowitz received a 1990 Nobel Prize in economics. And what Markowitz did was it's pioneered the use of mean variance methods and portfolio theory. Okay. Now, the book gets a little complicated on this, but we'll try to make it easier. And let's see how the book sets this up. This Markowitz model is going to be the following. We're going to consider the following optimization problem. What do we call it? A portfolio selection problem. Okay, good. And the problem will be to find the weight, W1 to Wn, of each of n assets in our portfolio so as to minimize. Now, Markowitz put this 1/2 there. This 1/2 is just to make things easy. The notation a little simpler. We're going to minimize the following. I equals 1 to n. J equals 1 to n. Wi, Wj, sigma ij. So here's what we're doing is we're minimizing. So here what we're really doing is we're minimizing 1/2 times the risk. And that risk is measured by the standard deviations here, which are either variances or these are variance or covariance here. And we have, this is a constrained optimization problem. We say that subject to the sum of the Wi r bar I equals 1 to n, equals r bar. And we also have that the sum of these weights, Wi, I equals 1 to n, equals 1. So we totally use up our budget here. And initially, we will allow Wi to be less than or equal to 0. This is for short sales. So we'll allow short sales. Okay. Now, what are we doing here? When you look at this, we're trying to minimize if we look at our portfolio diagram here, what are we doing? We're going to take an R bar here and come across to this. And then this will be our sigma. Let me make this R bar hat. And this will be sigma hat here. Okay, so what we do is we try to minimize the risk subject to meeting a certain expected rate of return. Okay, so this is like we're looking for an efficient point on that frontier. Now, this gets a little complicated, but bear with me on this. Okay, so the 1/2 the coefficient 1/2 in the objective function is just there to simplify the algebra. And say that the optimal solution, that any solution x star that minimizes f of x is the same as the x equal x star that minimizes c times f of x. Okay, and this is a non-negative constant. So putting that in the objective function doesn't do anything. Now, the other thing to note is the following. Note also that our problem, this portfolio selection problem, is an equality constraint optimization problem. Okay, and we have nice methods to solve equality constrained optimization problems. This implies that it can be solved by the method of Lagrange multipliers. Okay, so we're just going to explain something about Lagrange multipliers because the book goes over that. And this is this idea, this method of Lagrange multipliers is an old method due to Lagrange. This comes from the 1760s. And you might have had that in your calculus. But we'll develop it here. It's no problem. Okay. Okay. And we'll say basically the idea is to convert or trick, as it were, an equality constrained optimization problem into an unconstrained optimization problem. Okay. And then we'll see that it's easy to analyze an unconstrained optimization problem. Let's see. Let's look at the method in general. And why don't we say, the way we do this is that we multiply constraints by Lagrange multipliers and you can think of these Lagrange multipliers as being prices or penalties. And throw them in to the objective function. So basically the idea is the following. You can either solve the equality constraint optimization problem, optimize something subject to a constraint, or you can multiply the constraints by a price or a penalty and subtract them off the objective function there. So you can take care of the constraints in either of two ways there. Okay, so let's look at this. Let's look at this general method of Lagrange multipliers. Okay, now suppose our original equality constraint optimization problem is as follows. Say, find x equals, say, x1 through xn. So we have n decision variables in some set x, some feasible set x. That set x could be non-negative values of the x's, so as to minimize or max, doesn't matter here, some objective function of these n variables subject to gi of x equals bi, I equals 1 through m. So we have m constraints. We have m constraints, n decision variables, x and x, some set x. Okay. Now, let's call this problem, this is our original problem, let's call this guy call this problem P. This is our original problem. Let me turn that over a little bit. Okay, so that's our original problem. Now let's consider another problem. Related problem. And this related problem is going to be our Lagrangian problem. It's going to be find x equals x1 through xn, and lambda equals lambda 1 through lambda m. These are our Lagrange multipliers. Okay. So as to we'll say min or max, it doesn't matter. We can do both things. F of x minus the sum of lambda I equals 1 through m, gi minus bi. This you could think of this gi minus bi as having a gi x squiggle equals 0. So this is an unconstrained optimization problem, subject to just x and x. And we'll call this guy problem P prime. So this is our Lagrangian problem, problem P prime. Now we want to know when is the solution of P prime a solution of P? So the critical question we ask, and we'll answer it right away, is when is the x star and an optimal solution of P prime, also an optimal solution of our original problem. P. Okay. Now, we can answer this question as follows. Now, first note that since P prime is an unconstrained optimization problem, a necessary condition for optimality is the following. When we consider a function of one variable, then what is the necessary condition for optimality then if we have an unconstrained optimization problem? Then we know that we set the first derivative equal to 0 and solve for x. And so here we have more than one decision variable. So we have the following. What's an analog of that? So it takes the partial of the Lagrangian with respect to x1 equals equals the partial of that Lagrangian with respect to xn equals the partial of the Lagrangian with respect to the Lagrange multiplier, and this is true for all of the Lagrange multipliers up to m, d lambda m. Okay. Let's call this equation star. Now, so star is simply an n-dimensional, n plus m dimensional extension of the necessary condition say f of x equals 0 for f prime of x equals 0 for a single variable optimization problem. Okay. So if we're minimizing here, we know the following. Let's see. Let's look at this. Graphically, if you're looking at a one-dimensional problem, it's easy. Good. We can look at this. Suppose we're minimizing. We have f of x, x And then this is a convex function. So it goes down. The slope gets less negative. The slope goes to 0 here. This is at our x star. And this is f prime x equals 0 here. So if we look at the first derivative equal to tangent here, we can see that that tangent is increasing. If we were maximizing, we would get something that would look like the following. Now, what happens is we start off very positive, and we get less positive. At the optimality, we go to 0 here. So say f prime x star. Then we start decreasing. Here. So the first one is we're minimizing. The second graph we're maximizing. Now, so we have this necessary condition. So let's plug it in. Let's see. Now bear with me because there's a little bit of algebra in the book. Now, those are necessary conditions, that those partial derivatives equal 0. But what's a sufficient condition? Well, one set of sufficient conditions for optimality and what we mean by optimality, we mean when is the an optimal solution x to p prime an optimal solution to p. We'll say the following. If f of x is a differentiable so its derivatives exist, convex function so this function looks like this, defined on x, let's write that x a little better, for a min problem or a concave function for a max problem and each constraint GIX I equals 1 through m, so each of our m constraints is linear then any X star that is optimal to P prime is also optimal to our original problem. P. Okay. So any solution that satisfies star that equation star, which was just the partial derivatives equals 0. Okay, next we're going to go right into and show, next we're going to do the application. Let's apply this to the portfolio problem. Next time we will apply the Lagrange multiplier method to our portfolio selection problem. Okay. Okay, I apologize that we have a lot of gymnastics today, but I think they're relatively straightforward. Also, I really don't plan to have this kind of stuff on a test. So this is just for your general information. Okay, thank you very much. We'll see you tomorrow.